Yeah, so welcome to this second to last part of the workshop week here at Unisense. So my name is Tage Dalsgaard. I'm an application scientist here at Unisense. I've been here for 5 years and working a lot with biogeochemistry and microbial ecology applications. One of the things is the microprofiling system, which I'll show you here in a moment. I have a setup, and my intention is to show you sort of the individual parts, and then to calibrate the sensor and to measure an oxygen microprofile in a sediment core. So to do that, yes, I'll share my screen and show you the setup. Here it is. Yeah, what I have here is all the different parts that make up the microprofiling system altogether. So the central part, of course, is the microsensor. This is an oxygen microsensor, 100 micrometer tip diameter that I will use, and I have a backup one as well, in case I make a mistake. There's a micromanipulator here. This is a manual micromanipulator, but it's mounted on this motor stage, so the motor can drive the whole micromanipulator up and down with the sensor mounted out here on the tip. It can go in steps of actually below 1 micrometer at a time if you want that. Nobody needs that, but it can do it. This is mounted on a sort of a tilting plate in the back here, so you can go in at different angles if you need to. The motor is controlled via the motor controller. That's the one on the bottom here, the instrument. There's just a simple cable going up to that, and it plugs into the computer with a USB cable. On top here, I have the FX6 Uniamp, which is an amplifier. I have 2 oxygen sensors connected here on the picoamp channels. Could also connect 2 pH redox or electric potential sensors and 1 optical sensor. And then I have a temperature sensor mounted as well, because I want to use the temperature compensation for this. So these are the basic parts, and then I have a sediment core as well, which I'll get out in a moment. For now, I will just start the software. So I'll start the profiling software. The sensor trace suite consists of these different parts. Profile is one, rate is another one. That was the one Line used for the microaspiration. Then there's photo, which is for the photosynthesis measurements. And then there's logger, just for logging data over time. Logger is free, whereas all the others require a license. Now, when you start the software, just as Line did, you will see it looking for any Unisense instruments connected. And it found the FX6 Uniamp here, showing the serial number. It also discovered that there are 2 oxygen sensors connected here on channel PA1 and PA2. It suggests the unit micromoles per liter, and I'm happy with that. But you could, if you want, choose different units, partial pressure, milligrams per liter, or percent saturation, or whatever you want. It also found a temperature sensor, and I'm happy that it works in degrees centigrade. That's what I'm used to. And there's the pressure sensor, which shows the atmospheric pressure today. Down at the bottom here, it has found the motor controller, which will operate the motor on the microprofiling system. When you're happy with this, you have set the units you want. You can actually also give them names here, the sensors, if you want. You don't need to. And then you can click the Start Experiment. And that actually just means create a file. And I will create the file here in this one. I'll just call it number 2. And then it creates the file. From now on, then everything you do in the software is automatically saved. There's no save button here. So as soon as you do anything, it's saved. It then warns me that only micromole per liter as unit will allow you to do data analysis, but I am working in micromoles per liter, so I'm happy with that. So the different parts of the software, I'll just walk you through the individual tabs up here. Start down here where you see the live data. So this is the live data view. Here you can see all the sensors connected, all the channels. They show their values in millivolts or in calibrated units, depending on what you have chosen. You can choose that out here in the calibrated or not calibrated, and it shows the pressure of the atmospheric pressure today. So I just go this is a little bit up here where there's a calibration. I'll make a new calibration. This sensor is actually calibrated, but that was yesterday, so I'll make a new one today. There's another sensor which is not calibrated, so it has the red X here indicating that. Before doing the calibration, I'll just step through the different parts of the software. If we go left to the settings, you'll see the same screen as we had when I started the file, except that you can now not change anything. You can see what you have selected, but you cannot change it anymore. Going to the motor settings, you can see what motors are available. We have one for the Z-axis here, which is the vertical axis in our terminology. It has a motor connected, whereas there's no motor connected to X and Y axis. But you can actually connect both 2 and 3 motors to this, so you can have automatic profiling in 2 or 3 dimensions if you want. The profiling is where we record the profile. I will get into that after the calibration. Visualize is where the profiles show up when you have measured them. Activity is where you can do calculations on specific activity in the sediments and fluxes and so on. This is what I will show in the last presentation today. And comment, this is where all the events are recorded with a timestamp, and where you can also write your own comments if you want. Okay, going back to calibration, what I need to do now is I need to make a 2-point calibration of the oxygen sensor. I would like to make a 0 and 1 known concentration. Now for this, I have calibration chamber here, which has been bubbled with air, but I'll just make sure it is saturated by letting it bubble. Then I'll put my temperature sensor in and the oxygen sensor as well. Okay. Going back to the software. Now I need, first of all, I'd like to show you down at the bottom here in the live view. So I will now focus on sensor 1, which is the one I'm calibrating. So I'll just deselect the others so they don't confuse everything here. You can see now the signal here. Everywhere in the software you can click and drag, and you can zoom in to see the signal and keep zooming in. You can double click to zoom out again, so that's very handy. If you choose the Y zoom here, you can actually just zoom in the Y direction, so you can keep zooming in on your signal until you can see it sufficiently well to know if it's stable. I think this is stable, more or less, so I just need to record the value now. I need to enter the concentration in the water, the oxygen concentration in the water in the calibration chamber. And to do that, I'll use the oxygen tape. Now, first I'll go down here and select the temperature sensor as the temperature input. It's 21.69 degrees, so that's fine. Go into the oxygen table. I now need to tell it, I need to enter the temperature manually here. So that's 21.6 degrees. The salinity I will be measuring in is 23. It's from the Bay of Aarhus, yeah, oops, like this. The pressure of the atmosphere today is 1002 millibars, which you can see down here. So I'll just enter that. And the concentration of my calibration gas that I'm using is standard air, so that's 20.946%, or here is written in ppm, and that gives a concentration of 237.8 micromoles per liter. I'll click apply, and it's transferred to this window here. Then I just need to add a point. I'll just clear first. I need to clear the old calibration, so I get a blank screen here. Then I can add my point. So now I have one end of the calibration curve. The other end of the calibration curve I will get from a ascorbate solution. I have one here, which is ascorbate has an extremely high oxygen consumption potential. So it's always an well, at least for a week or two after you've made it. I'll put the sensor in, and you will see now the signal is decreasing down here in the live view. The Y zoom is clicked, so I can just click and drag, so I can zoom in and see if it gets stable. It just takes a little while to respond. Normally, these respond within 90% respond within 5 seconds or so, maybe a little less, 3 seconds now and then. I just have to wait for a full response here, and that is about now. I think it's become stable. Then I will change the known value here to 0 because it's anoxic. and then just add point. Once I've done that, I just need to click the Save and Use Calibration, and then the sensor is calibrated. See, now a second calibration showed up here, and this is the one that is in use. It shows the timestamp and everything. Now, what I also want to do is, in case there's a temperature variation, I want to use this temperature compensation of the Uniamp. Before doing that, I'll just take the sensor out and just get rid of the ascorbate by washing it. That. Okay. Yeah. So now the signal has jumped back up again. So I want to use the temperature compensation. There are these two, as I mentioned yesterday, the solubility temperature compensation and the sensor temperature compensation. The sensor temperature compensation depends on an A number, so that goes into the formula that compensates for the temperature changes. And that A number you can see down here, that is saved on the EEPROM on the sensor, so it's automatically loaded into the software, so it's the correct temperature compensation factor I'm using. Okay, with that said, then I'm actually ready to measure a profile. But before I can do that, I need to get my sediment core arranged and get it where I need it. So let's get rid of the calibration chamber. And so here's the sediment core. Yeah, and the sensor. And now the trick is, of course, to take the sensor out of the protection tube gently without breaking it, mounting it in the micro manipulator here, like that. Okay. Now, as I discussed yesterday, it's important to have a well-mixed water column, and I will do this today by bubbling the water, the overlying water, with air gently, so they'll create some water flow and maintain a constant oxygen concentration. So I have a stir pipette here, and I have air that I would like this. Okay. And then put this one into the okay. So like this. I can just zoom in a little bit to see what's happening. So now I have the pasteur pipette 2/3 into the water column. It's bubbling air. So the air bubbles pull the water along with it and create circulation in the overlying water. And the sensor is now mounted and ready. And now it's just to get the sensor down to close to the sediment surface. There are different ways of doing that. So I'll just try to keep my sensor in screen here, like this. Yes, so just before doing that, I will go into now the profiling part here. It's where you can see the different things to see. Over here on the right-hand side, there's the motor control. So the actual position of the motor is 0 at the moment. That's fine. Over here, you'll set the parameters needed for the for profiling. What I will do first is I would like to find the sediment surface, or to get the sensor tip close to the sediment surface. The first thing I do is start visually looking at it and moving the sensor with the coarse adjustment screw here until I think it is more or less close to the sediment surface. That's not so easy to see. A microscope would be better. Now, when I think it's close, then I start watching the signal down here now. This is the signal from the oxygen sensor. So when I now move the sensor slowly down the coarse screw, then when I get into the sediment, I know oxygen concentration is lower there than in the water, so it should decrease. takes a little while and some patience. There it is. Okay, so now I'll go back just a millimeter or so, like this, and the signal should come up. More or less. Go back a little bit more. And just a little bit more like that. Okay, so now the sensor tip is placed just a millimeter or so above the sediment surface. Then I need to define my profile, figure out what I want, how it should be measured. So a profile consists of a number of measurements at the different depths. Yeah, so what it has up here is there's a starting point, which is 0, an end point, which is set as 1000. I think the oxygen penetrates a bit more, so I would set it to 3000 micrometers or 3 millimeter in the first. The step size that will be, so a profile consists of moving the sensor, stopping it, waiting some time, and then recording a data point and then move on. And the step size here I want to start with is, let's say we start with 200 micrometers, so 5 measurements per millimeter. The safe distance is the position the sensor will be pulled out to when the profile has finished. So that's nice if you leave it to work on its own and go away for coffee, then the sensor will be taken out to a safe position. I'll just set this at 0 because then I know it'll just be taken back to the surface. There's a sensor angle. So if you for some reason cannot get vertically into the sediment, but need to go in for an angle then the software will calculate the vertical distance of your sensor, which is the relevant parameter for calculating fluxes and so on. But I'm going vertically in, so I'll go with 0. Then the wait before measure, that is the period that the sensor will stay at a position before it takes the measurements and moves on to the next. And I think for this sensor, 5 seconds is okay. It's probably a little bit on the short side, but we'll see. The measure period, so that is the period it waits after reaching a position before it takes that is the period that it analyzes. So after 5 seconds, it will measure for 1 second. That is, it will measure about 20 data points, take the average of those and save that together with the standard deviation of these data points. You can choose to have several replicates at each depth if you want. I'll just leave it at 1. If you have chosen several, you can set a delay between the data points in seconds here. And then if you want to run several cycles, that is in this case several profiles after the other automatically without interfering, you can increase this number. But I put it at 1. I just want to make 1 profile. So far so good. Then over here you can see all the sensors available, and I want to measure with sensor number 1. So I will deselect sensor 2 and the temperature sensor and the pressure sensor. So those will not be recorded together. And you'll see in a moment that it's nice only to have sensor 1. Then down here I have to check that my position is 0 because I want to start at 0, and it is 0, so that's fine. You can manually move the motor if you want, so you can move the sensors up and down to a certain position or in steps if you want to do it manually. But I'll just start the profiling now and let's see what happens. I think everything is set. So now the sensor is moving, which you cannot see, of course, because it moves in very small steps. No, I didn't hit this one. Sorry. Now it's moving. Yeah. Okay. So you see, this is the first data point collected. Now it's moving in steps of 200 micrometer and will collect the next data point. Now this looks very noisy, but if you can see the horizontal scale, you can see it's a very expanded scale. But now it's getting into something lower. I'll just close this one. So we're now moving into the sediment. So when you observe this while you're sitting here and waiting, you can maybe see, I want to do a different. I want to change the step size or the end depth or whatever. So you can do that as you go along. As long as you haven't reached the final or the end point here, you can make changes as you want. So maybe we should go to, it goes really fast. So I'll go to 100 micrometer steps now instead. And then you can see the step size will now decrease. And at some point very soon, we will get to the to 0. You can always, if you choose calibrate down here, you can see the concentration in micromoles per liter here being shown. We are very close to 0 now. Yeah. And then depending on how well you've defined your 0, see, I'm now a little bit below 0 now, and then minus 0.04 and so on. But now the profile becomes vertical. That means that we are now in the anoxic part of the sediment. There's no changes anymore as we go deeper. So there's no reason to go any deeper. So you can just click the stop profiling. And it asks if I want to return to the safe position. Yes, I would like that. And now the motor is pulling out the sensor again. So that's all there is to making a profile. I mentioned sort of the waiting time before making a measurement. And you can see down here now, if I click hold, then we can see it a bit more close on the data. You can see it's going sort of in steps down. And if you look at one of these steps, you'll like to see that it actually becomes stable before it moves on. It does more or less. If we just click the Y zoom away, I can just go in and have a look at these. So you see, well, it's almost stable, but I think a good profile, you would, it's quite okay. It's quite flat here. So it has stabilized before it took the measurement. So the measurements should actually be good. You can also zoom in on this data as you are measuring, and you can change the wait before measure if you discover that you have chosen a too short or too long period. Yes. So that's it. Now we have a profile. Then it's available in the visualize. All the profiles will show up here in visualize. I will just, I think I'll just make one more while we are at it. So I'll just move the sensor just millimeter horizontally so I don't go down in the same hole. And now I will start the profiling again. I think I'll start a little higher. I'd like to go a little bit higher. So I just pull the sensor 300 micrometers up before I start. Set that to be the home position. Now it's 0. And then I will start the profiling again. And now I'm profiling at 100 micrometer intervals. I would like to measure a really nice profile that we can analyze later. Okay, while this is, now you'll see up here that new profile is growing. There'll be a red dot coming below this profile selection text. Here it comes. So new profile is coming here now. Because I would like to get sort of this vertical part in the overlying water, but maybe I didn't get that. Probably not. No, it's decreasing. Okay, while it's recording, I want to show you. So it's still not available in the activity. In the visualize, sorry, and the activity, you can now select the profiles you've measured and do the analysis on them. But this is what I will do in the presentation that, later today. Let's go back to the, see now it's nicely growing. So it's a relatively high activity in the sediment. The oxygen penetration is only in the order of, let's see, if the sediment surface is around here, that is about 700 micrometer down to about 1900. So that will give about 1.2 millimeter of oxygen penetration. So that's typically for a coastal marine sediment as from out in the Aarhus Bay here. When you're measuring profiles, they're accumulating over here, so you can see them one by one as you go along. Now, I'll just wait and let the profile finish. And then once that has happened, I will export the data and show you how you get the data out in Excel. It's a very linear decrease in oxygen until the very bottom. And that indicates that as oops, I did zoom in, sorry, that the linear part indicates there's very little production or consumption of oxygen, whereas the curved part here indicates that there's a consumption. And what appears to be the case here is that most of the consumption takes place at the very bottom of the oxygen zone. But that's how it is. The sediment has been taken in to the lab about 3 months ago or so. So it's probably not very rich in organic matter anymore. So that means that electron donors come up from the sediment below, and you have the high oxygen consumption at the bottom. But I think this is now very close to being vertical. Let's take another couple of samples, and that's it. And the last one. Okay. Yes. I will stop the profiling here and pull out the sensor. Then in the visualize here, you can now see both profiles here, and out here, here you have the export profiles. I'll choose an Excel file. I'll go into the data files here, and I'll call it 2, just like my profiling file. And the Excel file is here. So what you get here is you get a data sheet for each of the profiles. In each of the data sheets, you get, in this case, you get the depth in micrometers. If you had done a 2 or 3D profiling, you would also get the other coordinates for your data point. There's a time stamp. There is a raw value in millivolt for the sensor. There's a calibrated value for the sensor. And there is the standard deviation for this value here. The same you see for the second profile I measured. Now these are all in 100 micrometer intervals. Devices show you what instrument you've been using, what sensors and so on has been connected, and what units you've been working with. Calibration data, they contain the 2 calibrations available. So the one from yesterday that was already there, and the one I made now. Comments that says what has happened during the experiment with a time stamp, and miscellaneous. That's sort of just some information about version numbers and so on. So you get all the data out in Excel, and you can do your plotting afterwards if you want, and calculations and so on. And by that, I think I'm through the demonstration. I'll be happy to answer questions if there are any. What is the best way to complete a profile using an electrode with a reference electrode? Well, the reference electrode, so that would be a pH electrode, a reference, or a pH, redox, and electric potential. They require an external reference electrode. And if you're using that, the external reference electrode just needs to be in the same water volume as the measuring electrode, for example, a pH electrode. So if I was measuring with a pH electrode in this sediment core, I would just dip the reference electrode into the overlying water, just like where I'm bubbling. It does not need to go in together with the measuring electrode. And it should not go in together because it's obviously too big and bulky. But there needs to be an electrical connection between the tips. So it has to be, in this case, seawater that's electrically conductive. So it just has to be in touch with the same volume of water, the 2 tips. Yeah, we can. The question is if we can color the glass tip, so it's easier to see the sensor, and we can do that. We can put some. I think it's porcelain paint actually that is baked onto the glass surface, so it becomes black, and then it's really resistant to scraping and so on. So you get a black glass sensor, so we can color the tip, and then it's easier to see, especially people using the in situ instruments, the underwater meter that are diving with the sensors, they like to have the black sensor tip to be able to better see it with goggles on and everything. In the lab, if you have a stereo microscope, you don't really need the black color, but it cannot be done, of course. So if the sensor tip should be at the sediment surface or slightly above the sediment surface when you start the profile, well, I think it should be above the sediment surface, because I always want to be able to see the diffusive boundary layer, and that is above the sediment in the water. So start a little bit higher. I know those that I measured today, they were really close. I think if I started up 0.5 millimeter higher, it would have been better, because then I could see the vertical part in the water column and the diffusive boundary layer and the sediment. Well, what concentration of sulfide will interfere with the oxygen measurements? I don't have a really strong answer on that. It depends on the concentration and also on the exposure time. So in most cases, if I measure oxygen profiles like I do here, then I just work in the oxyc zone and slightly below the oxyc zone. And there sulfide is often normally very low. Then you don't see an interference. But if you go deeper and the sulfide concentration will increase in the sediment, then you will see that your oxygen sensor starts to drift negatively, give a negative signal, and then it recovers when you get it out again. But it depends on how long you keep it there and what the concentration is. But I don't have a strict answer to that. Yes, and the comment on the software works great. Yes, it normally does. Yes, and we try to keep it up to date and to follow all the whatever Microsoft figures out it wants to change how communications goes on the USB ports and all that. So yeah, so it's important that you actually do update your software now and then, because now and then suddenly a change comes from Microsoft, and then we have to incorporate that in our software. And if you then update your Windows, you may run into problems. So please keep an updated software. That would be important. Yeah, that's a very good question. I'm not quite sure where this. So the question is if we recommend poisoning the oxygen sensors with sulfide before the first calibration. I don't think we recommend that anymore, and I'm not sure why it was recommended either. It's I think it came from Aarhus University, where they had an experience that might be a good idea. I think you have to try it out and see what works best for you. It's not a recommendation from us now, at least. Okay, you haven't noticed difference. That's good to hear. Yeah. Yeah, so the question is if the flow of water can damage the sensor tip, and the question is no. As the answer is no. That we haven't seen that happen. We also have sensors mounted on in situ instruments that are being lowered from a ship into the waves, and where the waves smash onto the instruments, and the sensors are not harmed by that. So we also mount our sensors in flow cells, where we can have a very strong flow in sort of a T-piece, where the sensor tip sits right in the middle of the flow through cell, and it's not harmed by the flow rate. What happens if the connection between sensor and software is accidentally interrupted during measurement? Well, it depends on for how long you interrupt. We've actually now changed the software so it can accept a certain amount of interruption. So it is now patient and waits and tries again. I'm not quite sure how long that waiting period is actually, but you should try to avoid interrupting the connection if possible, of course. Yeah, it's yeah, that would be the best. But there is now a short time period that's allowed. Thank you very much for listening.